Welcome to This Explainer. Today, we are going to completely, radically reshape how you view the cosmos. We're looking at our place in the universe and, frankly, humanity's ultimate strategy for survival. We're going to journey all the way from the tiny quantum nature of particles right up to the existential timeline of human civilization. And then, we're going to conclude with an absolutely mind-bending strategy for outliving the stars themselves. Oh, and spoiler alert, the standard cosmological rulebook? Yeah, we're throwing that completely out the window. All right, so let's dive right into this core premise because it totally challenges our basic understanding of how the universe was even born. I mean, most of us grew up with this image of the Big Bang, right? Just a violent explosion expanding out into empty space. But the source material we're digging into today flips that entirely on its head. It suggests a reality that is, well, far more structured, deeply unified, and literally infinitely nested. What if the Big Bang wasn't an explosion at all, but a decay actually happening inside a black hole? To unpack all of this, we'll move through four main sections today. First, the black hole multiverse. Second, the 10,000-year bottleneck. Third, the stellar engineering paradox. And finally, the red dwarf exodus. We've got a ton of fascinating ground to cover, so let's just get right to it. Section 1, the black hole multiverse, rethinking singularities. Let's start with the literal architecture of reality. And while we're at it, let's debunk a major physics myth. So, there's actually a massive, fundamental contradiction in modern physics. The old, traditional view tells us that black holes contain a singularity, a single point of infinite density. But if you look at quantum mechanics, specifically the Pauli exclusion principle, it tells us that matter literally cannot overlap. Think of it like trying to crush a jar full of solid marbles. You can push all you want, but eventually they just can't pack any tighter. Because matter can't infinitely overlap, singularities can't actually exist in reality. They're really just mathematical red flags telling us, hey, general relativity breaks down here. Instead, the inside of a black hole actually contains a finite, ultra-dense object, kind of like an extreme neutron star. The event horizon only forms because this object is so unbelievably compact that its gravity traps light, not because all that matter magically vanished into a single mathematical dot. Okay, so if there's no singularity, where did all our matter actually come from? Well, instead of fundamental particles just popping into existence from nothing, everything arises from a cascade of divisions. It's like a massive cosmic family tree starting from just one single primordial Z particle. This Z particle decays, and in that very first initial decay, space-time and energy are co-created. They're twin, inseparable products. From there, the energy just cascades downwards, dividing again and again into smaller, lighter fragments. And that eventually gives us the quarks, the leptons, and the bosons that make up, well, you and me and everything around us. So actually, scratch the explosion idea, it's much more accurate to call it a fragmentation tree. And this grand model led us to what is easily the boldest conclusion of the whole theory, the fractal multiverse. Listen to this. If the Big Bang was really just the decay of a single primordial particle, that decay had to happen somewhere, right? Specifically, it happened inside a black hole that was located in a parent universe. Meaning, our entire universe is the interior of a black hole. Mind-blowing, right? And suddenly, cosmic expansion doesn't require any mysterious dark energy. The expansion of our universe is literally just that parent black hole accreting mass and growing in its own reality. It's exactly like a cosmic nesting doll. Black holes within black holes, building an infinitely cascading fractal structure. But here's the catch. This cosmic nesting doll idea creates a massive existential crisis for humanity, especially when we look up and notice the eerie silence of the night sky. If universes are constantly birthing inside black holes over and over, the multiverse should be infinitely ancient. So where is everybody? This brings us straight to the famous Fermi paradox. If this has been going on forever, why haven't we seen massive, galaxy-spanning ancient alien empires? Section 2, the 10,000-year bottleneck, the Great Filter. To figure out why the wider cosmos seems so incredibly empty, we really need to look at our own historical timeline. Think about it. For hundreds of thousands of years, humans lived in this very stable, low-tech, kind of forest phase. Then it took a mere flash, just 10,000 years, to go from living in cave dwellings to literally splitting the atom and launching rockets into space. On the grand scale of the cosmos, 10,000 years is absolutely nothing. It is a microscopic blink of an eye. We went from stable survival to holding civilization-ending technology in our hands almost overnight. So here is the absolutely crucial takeaway. Technological civilizations appear to have a natural maximum lifespan of just about 10,000 years. Once you hit that crazy technology threshold, you face a severe bottleneck, and there are really only three possible fates. 1. You destroy yourself through war or maybe rogue AI. 2. You collapse back into that stable forest phase. Or 3, if you are incredibly lucky, you survive the bottleneck and transcend into something quiet, advanced, and extremely long-lived. This perfectly solves the Fermi paradox. The galaxy isn't filled with loud, ancient empires. No, it's mostly full of quiet forest dwellers, peppered with occasional brief, loud flashes of doomed technology. Flashes that just don't last long enough to ever overlap with our own brief flash. Section 3. The Stellar Engineering Paradox. Saving our star. Now, if we actually want to be one of those super rare civilizations that transcends this bottleneck, we've got to deal with the ticking clock of our dying sun. I know our sun seems totally eternal to us, but on a cosmic scale, sun-like stars are just short-lived, loud sparks. If you want to play the really, really long game, you have to look at red dwarfs. These stars burn their fuel incredibly slowly. That gives them a lifespan not of billions, but of trillions of years. A planet stationed around a stable red dwarf, that gives a civilization billions of attempts to survive that terrifying 10,000-year bottleneck. Now, you might be wondering, why not just fix our own sun? Like, could we just feed it a gas giant like Jupiter to keep it alive? Well, apologies to Jupiter, but sacrificing it only adds about 0.1% of mass relative to the sun. That yields a completely pathetic 10 million extra years of life. I mean, in stellar terms, that's practically a rounding error. Actually, it's worse than that. Feeding the sun literally dooms us faster. See, adding mass to the surface increases the pressure on the core. That higher pressure speeds up the fusion reaction, which causes the star to burn through its fuel way faster, ultimately shortening its overall lifespan. Plus, the sun isn't a giant mixing bowl. That fresh hydrogen you drop on the surface doesn't even reach the core where it's actually needed. Now, the source notes you could theoretically extend a star's life by removing mass, literally slicing plasma off the star with magnetic fields to lower the core pressure. But here's the paradox. Slicing the sun requires millions of years of patient, stable, continuous work, and time is exactly what a 10,000-year civilization simply doesn't have. Section 4. The Red Dwarf Exodus, the Ultimate Solution. This brings us to the grand finale of our explainer, the only real, viable way to survive the fractal multiverse long-term. Forget terraforming Mars. The ultimate survival plan is so much more ambitious than that. Step 1, we encase the entire Earth. I'm talking oceans, atmosphere, crust, and core, all wrapped inside a massive, protective spaceship shell. Step 2, we apply a tiny, sustained thrust to this shell over millennia to physically break the Earth out of the solar system. Step 3, we fly our entire encased planet across interstellar space until we arrive at a long-lived red dwarf star. Inside that shell, totally protected from acceleration, radiation, and the freezing void, life just continues on normally for the tens of thousands of years the journey actually takes. But once we finally arrive at our new red dwarf home, we can't just park the Earth anywhere. Red dwarfs are notoriously volatile in their youth, and they tidally lock their planets, which means one side always faces the star. So our newly encased planet is going to need a few specific things. First, an incredibly dense atmosphere to constantly circulate heat from the day side over to the night side. Second, a super strong magnetic field to block the star's intense solar flares. And finally, an orbit right on the extreme outer edge of the habitable zone, just to avoid a runaway greenhouse effect. If we hit all those conditions, boom! We secure a home for literally trillions of years. I want to leave you guys with this final, really provocative thought. We started all of this by looking at a multiverse infinitely cascading with black holes, right? And we asked, why is the sky so silent? Well, what if the silence of the cosmos is simply because advanced civilizations eventually figure this out? What if the ones who actually survive the bottleneck don't bother building loud radios or giant flashy Dyson spheres? Instead, they encase their planets, pack up everything they hold dear, and leave quietly for the long, slow burn of the red dwarfs. Perhaps in a fractal multiverse, ultimate survival doesn't mean conquering the galaxy. It means going quiet, scaling down, and playing the longest game of all.